Here we go. Banked corners with friction. So more to do with banked corners, but the more realistic case where there's friction. So in this kind of situation, there is a maximum and a minimum speed that's possible for uniform circular motion. The friction can apply enough force to help it stay in circular motion, even if it's going too slow or too fast. So the two cases here, too slow and too fast, to consider those, right? Case one is if you're going too slow to the normal force of the ramp to be the perfect amount for uniform circular motion. And then the other case is if you're going too fast, right? For the normal force to be the perfect amount. So in these situations, we're going to look at free body diagrams for them. And so this is what we're looking at. In our direction system, we're going to define the direction system as horizontal for the x direction because that's the direction of the centripetal acceleration. So that makes the true up and down be the y. Whereas lots of times with ramps, of course, we align the acceleration would be down the ramp. So we'd have the x direction down the ramp, right? So notice that little distinction there. In a scenario like this, the normal force y component isn't going to be matched up with gravity like it has in the past been. So what you have now is you've got a friction component in the y direction. So you're going to have your gravity and you have your normal force, but you're going to have a friction component in there. And notice, by the way, I didn't really reveal it earlier, but in this scenario, we're going to be slow. So the friction points up the ramp, as you see in the free body diagram. So that friction is up the ramp, and that's the too slow case because it's stopping it from sliding down, right? In the too fast case, basically all the same stuff, except the friction is going to be going the other way. Okay? So the friction is going to be pointing down the ramp, trying to stop it from sliding out and up the ramp. So very similar stuff otherwise. This guy here was what? Scan back up. For each situation, there's going to be a maximum and minimum speed that you can go. So let's look at slowest speed possible. We'll look at an example of a mass of 1,000 kilograms, 80 meter radius, angle of 20 degrees for the bank corner, and a coefficient of friction of 0.1. You might be looking at this thinking, hey, do we need that mass? You're starting to anticipate some of these things. And in fact, you don't need it for speed, but you do need it for forces. Same as when we did energy concepts in grade 11. So the first thing we have to look at is just would it just slide down the ramp if it was stopped, right? In which case, if it wouldn't, then the minimum speed, you can go as slow as you want, right? So let's look at our free body diagram for this thing. We're going to show the friction up the ramp. So that already has the calculated value in there. We still have our free body diagram with our direction system as usual, as we said on the other page or whatever. I want to put this part here right now. Oh yeah. So note that this free body diagram is not for uniform circular motion. I said it was like usual, but it's not, in fact, right? So the direction system, we're looking at the stationary direction system. So the preferred direction system is down the ramp, right? The vertical component off of the, perpendicularly up from the ramp would be 0 and so on. If it was uniform circular motion, what we're looking for is we know, because we're staying in a horizontal circle, we know that the vertically this way, right, straight up and down would be balanced out. Right, so that would be equated. Although I should add in friction would be included in that, I guess. But yeah. So with uniform accelerated motion, uniform circular motion, sorry, there is an acceleration component up perpendicular to the ramp, which is kind of a weird thing to think about. And you'll see it later on where you have your centripetal force and the component of it up the vertically, like here, right? So that component of the normal force is providing your centripetal force, and there's a component of that up off of the ramp. It's just kind of a weird thing to think about. So here we go. We got our net force in the y direction here is 0. It's not lifting up or down off the ramp because it's just sitting there. And we're just wanting to see if it's going to slide down or not. So we have our normal force, we have our gravity force, y component, and we're looking at the normal force then. being the opposite of the gravity. And so then we get our gravity component in the y direction component number there. So mg cos 20 or that value if you put the mass in. And so then we can get our friction. Okay, normal FF equals mu Fn stuff. So there's our friction value as labeled on the graph. And so we're looking at, of course, if that friction force is smaller than what gravity is providing, or say if gravity is greater than the friction force, then it would slide, right? So let's look at the x component of the gravity. And so it's, that those values times sine of 20. And so the gravity is like 3,351.8 newtons. So obviously, yeah, it's going to accelerate down the ramp. Okay, so there is going to be some slow enough speed that friction will help and make it be able to do uniform circular motion. Okay, so here we go. Slowest speed for uniform circular motion. The main thing is, of course, now we have the acceleration in the y direction vertically, like true vertical, is 0. That's our uniform circular motion thought process. Rid of that box there for us. So there's that direction system based on that idea. And at free body diagram as before, right? And so because we're in uniform circular motion, then we know that the, yeah, that's fine, I guess. F net in the y direction is 0. Anyways, in that y direction, I mentioned before, we have to include friction, right? So don't forget that thing. There's a component of friction in that direction. And of course, you have your normal force in that direction and the gravity force. So we can do those calculations, and that looks like this page here. So we're going to put numbers in here. We've got the gravity in as down of 9,800. We've got our friction force being the 0.1 times the normal force times the sine of 20, and our normal force y component being Fn cos 20, right? So that is, my delete button does not seem to want to work lately. Come on. Bear with me here. So that's the y component of the friction force, as I said, and the y component of the normal force. And so solving out here, we add 9,800 to both sides and end up with the 9,800 over there. Here we'd have a normal force in both of those terms. And so mathematically, we can common factor that out, end up with a 0.1 sine 20 times a cos of 20. And that's just a value, of course. We just divide that thing out. Okay, so divide out that number here. I'll just say whatever that is, divide that out. Just do it on the calculator, right? End up with a value apparently of 10,062.7 as our number. Okay, so that's our normal force. So then we can calculate our friction force. Okay, so our friction force is going to be 0.1 of that, so it's going to drop it down by a factor of 10 and just be 1,006.27. Oh, that was just, should have showed that earlier, but I mean friction, obviously just mu Fn, right? So FFX, oh, the X component of the friction force. That's for later, I guess, really. Okay, here we go. So here we go, uniform circular motion, right? So of course we know that the net force in the X direction is the centripetal force, and the net force is all of the forces added up. And so we've got that friction force X component that we just mentioned there a little bit, and the normal force X component. FC, we know, is mv squared over r. And then we have values for all this stuff, right? So we have values for the friction, and so we can get the X component of it. I don't have the free body diagram on this page, but I mean, we've done it enough times, right? So the friction force is there. So there's the 20 degrees, and so we're cos of 20, right? So FF cos 20, and same thing for the, very similar thing for the normal force, again, the components. Notice that both of these numbers here, messy numbers, are based on that 1,000 kilogram mass, right? And so quite literally at this point, you'd have m's on both sides everywhere. And so you'd say, oh, mass isn't needed. You could cancel it all out. Now, I gave the mass because it just kind of feels a bit easier. But really, this would have just been, m times g times whatever, right, in there. And yeah, so the m would just cancel out. Anyways, in this scenario here, in order to have the force, though, yeah, yeah, in order to have the force, you'd have to have the numbers, but it's the speed we're looking for, right? So this would be still an m in here, and it would equal to the mv squared over r stuff. So there's your m on that side to match up, and they could have canceled out, and multiply the 80 across, and take the square root and so on. I didn't show the algebra as much here, but I mean, obviously, you just do the 80 times across to get rid of that, and you would do the divide by 1,000, right? And that would give you whatever number that is, and then of course we just root both sides, and then technically plus or minus root of that, and we're just looking for the speed, so we just call it the plus version, right? So we get 14.1 meters per second is our speed. All right. So definitely a little weirder. The idea of the friction, contributing in multiple ways to the vertical and to the horizontal and so on. But I think the free body diagrams carry us through it. And so I hope that makes sense. I want you to, as part of the homework thing, practice whatever, calculate the maximum speed it can go without sliding. And so really the exact same stuff. It's just one little difference, right? That you have the friction going the other way, right? So just run the numbers, see what you get. There is a solution that can be posted afterwards. It's around 18 or 19, if I remember right. But yeah, you'll see. So that's the bottom one here. And then the two questions, there aren't as many with friction in the textbook for some reason. So I'm asking you to, do this question over again. If you had, what would or if the speed is increased, what coefficient of friction would be needed? Sounds a little bit of a, adjustment in how you tackle things, because I'm asking you for that coefficient of friction, but really the overall work is the same. It's just you have a different missing piece. And this one here, redo sample problem 2. Of course, sample problem 2 is in the textbook file that's online, or I put it there just for easy access for you as well. So it was a no friction question. And so I want you to, use that example and determine the minimum speed possible. So I put this one first because this is really the exact same as we did in the lesson. Try that, get comfortable with it, and then, maybe afterwards go to this one and tackle and get the maximum speed, see how you do. And then, of course, this one be a little different, but I'll leave it for you to give a try. All right, so that's all for today. Thanks for watching.